The first talk will be by Salvador Rosauro, and he's going to tell us about neutrino portals to dark matter. Please.
Okay, thank you very much. Good morning, and thanks to the organizer for giving me this opportunity and making possible this nice workshop in this beautiful city. So indeed, today I'm going to talk about some work my collaborators and I did on neutrino portals to dark matter. So let's start. As you know by now, dark matter is one of the few experimental signals we have for physics, for the existence of physics beyond the standard model. We have probed dark matter at very different scales in the universe. For example, with studying galaxy clusters through weak lensing, or the rotational curves of spiral galaxies, which were first observed to differ from the ones expected from the luminous matter by Vera Rubin. So in the end, at different scales, we have the matter power spectrum from also CMB measurements and baryon acoustic oscillations, and all of these together give us the dark matter relic density of the universe, which is around 0.12, and which translates into the fact that dark matter constitutes around the 25% of the energy budget of the universe. Nonetheless, all these probes we have for dark matter are all gravitational ones, and therefore they will never give us the true nature of dark matter if we assume it is a particle. So we need other kind of searches. For example, direct detection searches, which rely on the fact that dark matter would interact with nuclei and produce them to recoil. However, unfortunately, we don't have a positive signal in direct detection experiments, and we can only put upper bounds on this cross-section. Nowadays, the strongest one comes from Shinon-Wanton, and here we have summary plot with all the current and some future prospects for direct detection experiments, of course assuming that this is through thermal freeze-out and so on, which is something we will assume throughout all the talk. Now, we can also look for dark matter in indirect detection searches, where we probe the annihilation cross-section of dark matter into some standard model species, for example, into taus and muons, I'm showing here. And again, we don't have any definitive signal for these annihilations. So Fermi-Lat put some upper bounds again on the annihilation cross-section to charge leptons and other species. So now looking back at the standard model, we realize that in fact we have neutrinos there, which are the most weakly interacting particles we know of. And therefore, we could think that dark matter interacts primarily with neutrinos, and therefore is evading all our direct and indirect detection searches with charged leptons and quarks. Now, if this was the case, it is also important to know if these kind of interactions could be detected. So now I'm going to give a review of all the constraints we're going to take into account in the following models we're going to discuss. So even if we're looking for dark matter neutrino interactions, you will always need to take into account direct detection and indirect detection constraints, because at loop level, you will always be able to find an interaction between dark matter and quarks and charged leptons. And in fact, the direct detection constraints are very stringent, so they could dominate the phenomenology and the bounds. From cosmology, we will take the lower bound on the mass of the dark matter to be above 10 MeV, so that we don't change the measured effective number of neutrinos by Planck. And we will also take into account the effective parameter measured by Planck, this PA, which depends on the annihilation cross-section of the dark matter in the early universe, and which is basically measuring the energy injection of dark matter annihilations into, for example, electrons, the energy injection into the CMB, which would change the CMB anisotropies as measured by Planck. Now, regarding neutrino, assuming that dark matter annihilates into a pair of neutrinos, we will assume that this interaction exists, and that therefore dark matter annihilates in high density regions of the universe, such as the galactic center and the Milky Way halo, and therefore, when neutrino travels to the Earth, we have a monochromatic flux of neutrinos which get to our detector, for example, Super Kamiokande, and is detected. For example, the Super K collaboration puts upper bounds on this annihilation cross-section from the annihilation in the galactic center. And you can play this game with any neutrino detector you have. So now let's move on to the different models. And the simplest one you can think of is just taking the standard model. We will couple dark matter directly to the neutrinos of the standard model. However, from gauge invariance, you know that the neutrinos belong to an SU2 doublet of the standard model together with the charged leptons. And therefore, if we want to build a gauge invariant theory, we would need to write operators like this one effective operator here, where dark matter is coupled to the full lepton doublet. This is an effective operator, so lambda would be the new physics scale, and C alpha is a coupling with each one of the generations. Now, from this operator, it is clear that dark matter is interacting as strongly with the charged leptons as with the neutrinos. So it seems really bad news, because the indirect detection searches to charged leptons are much stronger than the ones from neutrinos. And from the annihilation cross-section, you see that the only difference relies on the mass of the given particle. For neutrinos, we can neglect their mass because they are very light, but we cannot do this for charged leptons. So let's see what happens when we study this model in detail. Here are some results. We have the new physics scale lambda against the dark matter mass. And here we have the bounds from BBN on an effective. And this is a coupling just with the electron doublet. These red colored regions correspond to bounds from Super K from the dark matter annihilations in the galactic center and in the Milky Way halo. The pink one corresponds to bounds from studying the atmospheric background in Frejus, Amanda, and Super K. And the yellow one is from Borexino, which is a solar neutrino experiment. We have some hatched region here, which are Fritter prospects. And along the blue line here, we recover the correct relic density as measured by Planck through thermal freeze-out. Above this line, this is ruled out because you would overproduce dark matter, overclosing the universe. And below, you would produce less dark matter. Now, there is one final constraint, which is this green region here, which is the constraint given by Planck on this P annihilation, this effective parameter. And as you can see, this is completely dominating the phenomenology and ruling out basically the whole parameter space where you can explain the dark matter. So as expected, Planck and Fermi-Lat are posing the strongest bounds. Now, if you couple dark matter only to the tau lepton doublet, in this case, there is an open window of parameter space here when the mass of the dark matter is smaller than the mass of the tau lepton, where obviously annihilations into tau leptons cannot happen. And in this region, you see that indirect neutrino detection searches are the only probes putting some bounds in this region of parameter space. However, it is strange that the dark matter would only couple to the third generation of leptons, and that its mass is smaller than the tau mass. Or at least we would like to have a more fundamental reason for that other than just avoiding constraints. So we would like to know if it is possible to avoid the coupling to charged leptons so that not in any way. And this is where we remember that another experimental evidence for physics beyond the standard model is the fact that neutrinos are massive particles, as discovered in neutrino oscillation experiments, and that therefore we need new physics to explain neutrino masses as well. So let's take a look into that, and the easiest way to explain neutrino masses is with a type 1 seesaw mechanism, where we introduce a given number of right-handed neutrinos, which are singlets under the standard model gauge group. That means that I can write a Majorana mass term for these right-handed neutrinos, which breaks lepton number into units. Now, if you assume that the Majorana mass term is much larger than the Dirac mass here, you can get that the light neutrino masses are inversely proportional to the Majorana mass, while the mixing between light and heavy states is basically the ratio between the Dirac mass and the Majorana mass. Now we go to neutrino experiments and try to explain the data there. And we assume that the Yukawa coupling is of order 1, and that neutrino masses are of order 10 to the minus 2 electron volts. And what we find is that the Majorana mass needs to be of the order of 10 to the 15 GeV, and then the mixing between neutrinos needs to be of the order of 10 to the minus 13. And this means that this scenario is untestable from an experimental point of view in current experiments or even future experiments. So we would need to think of something different from in order to have a more testable neutrino mass scenario. And in this direction, we can assume that we have an approximate lepton number conservation. In any case, the standard model has an accidental lepton number conservation. So in this sense, you can think of an inverse ISO scenario where you introduce Dirac neutrinos, which are again singlets under the standard model and have this Dirac mass here. But again, we can write a Majorana mass term for them. Now, if we assume that lepton number is an approximate symmetry, we need that this Majorana mass term is small. And what we find in that case is that neutrino masses, light neutrino masses, are proportional to the Majorana mass scale. And then the mixing between light and heavy states is independent of the Majorana mass scale. And therefore, even if the Majorana scale went to 0, in which case, of course, neutrino masses are 0, which is not in agreement with experiment, we could still have large mixing between the heavy and the light neutrinos. Now, given that for the dark matter phenomenology, light neutrino masses are not important, we will assume them to be massless from now on, and we will just include one Dirac singlet neutrino, whose mass is basically the sum of the Dirac masses. And in the end, we will have that the flavor eigenstate, the electron neutrino, the mu neutrino, and so on, will be a linear combination of the mass eigenstates, where this mixing matrix U is basically controlled by the mixing angle theta, which, as I said, can be large in this kind of scenarios. So in order to study the dark matter, what we're going to do in this case is couple dark matter directly to the singlet neutrinos to comply with gauge invariance, and then through this large neutrino mixing, we will be able to have a coupling between active neutrinos and dark matter. We will study this in two different cases, first with a scalar mediator, and then with a vector mediator. Okay. So for the scalar mediator, this is the Lagrangian we have. We have the Dirac dark matter, and the interaction term between dark matter, the scalar, and the singlet neutrino. We also have a scalar potential, but that's not really important. Note that this scalar needs to be more massive than the mass of the scalar needs to be larger than the mass of the dark matter if we want the dark matter to be the Dirac particle. But you could always have the scalar as the dark matter and chi as the mediator. Sorry. Also note that the dark matter and the scalar can share any U1, can have a U1 symmetry as long as they share the same quantum numbers, and that the scalar cannot develop a web so as to avoid dark matter neutrino mixing. So in the end, writing the sterile neutrino NL as a linear combination of the mass eigenstates, you get a coupling here specifically directly between the dark matter, the scalar, and all the massive neutrinos, both the light neutrinos and the heavy one. Now looking at the cross-section, annihilation cross-section to light neutrinos, it's easier to realize why we were looking for mass models where the mixing was large, as the annihilation cross-section is proportional to this mixing. Therefore, if the mixing was to be of order 10 to the minus 13, we could never explain dark matter through freeze-out in these kind of scenarios, because we would always overproduce dark matter. Now, from at the loop level, through these diagrams here, we can get couplings both with quarks and leptons. So therefore, we cannot neglect these terms here, because, as I said, direct detection constraints are very strong. So let's look at some results. In the left panel, we have the cross-section, the annihilation cross-section, as a function of the dark matter mass for two different couplings. And in green, we have the annihilation to electrons, in orange to muons, and in red to taus. And up here, we have the bounds from Planck and Fermi-Lat, which were previously ruling out the whole parameter space. So as you see, given that these processes only appear at the loop level, we succeeded in avoiding them. Now, on the right panel, we have, as a function of the coupling and the dark matter mass, and for different masses of the mediators, the regions of parameter space where we recover the measured dark matter relic density by Planck. Finally, we have in the vertical axis the mass of the scalar, and on the horizontal axis the mass of the dark matter. And along this blue line, we again explain the relic density. Above, we are overclosing the universe. And as you can see, the only constraints for this kind of scenario are those given by neutrino indirect searches. In particular here, this one comes on a super K. And future neutrino experiments, such as hyper K or Dune, could in principle even probe down to the thermal relic cross-section. We also have Darwin, but remember, this is a dark matter experiment. This analysis was using Darwin as a neutrino experiment as well. Now, for an incredibly large coupling at the perturbativity limit, you see that the bounds from Xenon 1 ton, even though they come from a loop process, they appear there and rule out large dark matter masses. But in general, we have that neutrino experiments are the best probe for these kind of scenarios. And by the way, this is the size of the neutrino mixing we need to get these results. Now, moving on to the vector mediator, here we include a set prime, a massive set prime, and we couple the set prime to the left-handed part of the singlet neutrino and to the right-handed part of the dark matter, so as to have anomaly cancellation. And again, we get, through neutrino mixing, the coupling between dark matter and light neutrinos. Okay, here is the annihilation cross-section. And again, you see this is totally controlled by neutrino mixing. And given that here the annihilation goes through an S channel mediated by the Z prime, we have a resonance in here whenever the mass of the dark matter is about half the mass of the Z prime, which makes the annihilation cross-section blow up. Again, we get couplings to charged leptons and quarks. In particular, we get this coupling between the Z prime and the charged leptons, and then we have kinetic and mass mixing between the Z prime and the Z, which basically induce an effective coupling between all the standard model fermions and the dark matter. So again, we will need to be careful with those. Now, some results again. In this case, the annihilation cross-section to charged leptons is slightly larger, but again, we get to avoid the coupling, the constraints from Planck and Fermi-Lat. And in the right-hand side plot, we have the lines where the correct relic density is recovered, and this peak here is nothing else than the resonance we had in in the cross section there. So finally, for the vector mediator, again in the plane of the mass of the mediator over the mass of the dark matter, we have the blue line corresponds to where we recovered the dark matter relic density, and the pink regions are the ruled out regions of parameter space by neutrino experiments. And as you can see, a large fraction of this parameter space is already being ruled out by these experiments. Now, although in the previous, with the scalar mediator, all this region of parameter space was ruled out because of dark matter stability, note that this is not exactly ruled out, but this is just that the dark matter would annihilate into a different channel, but you could still, in fact, into a 2 set primes, so it would be a vector portal. And as we were interested just in the neutrino portal, we didn't look into that region of parameter space. Again, Dune could, in principle, probe down to the relic density target for some regions of parameter space, and we find that Shino 1 ton places very strong constraints for large dark matter masses and large coupling. So I was super fast. In conclusion, given that unfortunately we haven't found any positive signal of dark matter standard model interactions other than gravitational, here we studied the possibility that dark matter is primarily interacting with neutrinos. And if this was the case, we wanted to know if one could avoid all these constraints. Now, if you do the most simple thing and comply with gauge invariance, which is something one should do, then you couple dark matter to the full lepton doublet in the standard model in a minimal sense, and then Planck and Fermi-Lat completely kill the model unless you have some flavor structure in the couplings, which of course you would need to explain, such as the coupling to the electrons is small and the mass of the dark matter is smaller than the given charged lepton. If this was the case, indeed, neutrino experiments could be our best probe to probe this kind of scenario. Now, taking into account that you need to explain neutrino masses in any case, you could take advantage of that and couple the dark matter directly to the singlet neutrinos. If the mechanism under the origin of neutrino masses is such that the mix in between light and heavy neutrinos is large, you could get to explain the dark matter abundance through thermal freeze-out. And in this scenario, indeed, neutrino experiments would be our only hope to probe the nature of the dark matter. Thank you.
Okay, we have time for questions.
So that's a very general question, or maybe when you talk about the neutrino mass mechanism that should exist,